Hey guys, and welcome back to chemistry. Today we're going to be finishing up our discussion of subatomic particles in the atom by talking about the neutron. So we've already talked about the establishment of the electron using Thomson's cathode ray tube, and then how the proton was first theorized that it existed, and then it was shown to be in the nucleus of the atom with Rutherford and his gold foil experiment. And now kind of moving forward, we have established that there is also a third kind of subatomic particle called the neutron. The neutron is just slightly heavier than the proton, but it is neutral, no charge. So all atoms except for hydrogen contain neutrons. If you look at this picture right here, we have one proton here and one bitty electron here, and then the neutron is about the same size as the proton, just a little bit, one electron really heavier. We'll talk about that in a second, just slightly heavier, but it is a neutral charge. All neutral atoms contain protons equal to their electrons. So as we look at these subatomic particles, protons determine what kind of an atom it is. If it has 3 protons, it's lithium. If it has 6 protons, it's carbon. We know an atom's identity based on the number of protons. The electrons, if the atom is neutral, are always equal to the protons. But the neutrons can vary. We'll be talking about that in just a minute. Protons are established as being in the nucleus of the atom with the neutrons. And the neutrons actually help create something that is collectively called nuclear forces, which help hold the protons together. Because as you may remember, like charges should be repelling each other, but we see that in the nucleus, we have all of these positive charges all grouped together. And so when we describe what allows them to stay together, the general term for that is called a nuclear force that allows for the establishment and then also the maintenance of that positively charged nucleus. As I mentioned before, the proton and the neutron are very similar in their masses. So what we're going to do right now is we're just going to look at this chart. I'd suggest writing a chart like this down in your notes. It's going to take us one particle at a time. So let's just look. We'll start with the electron. E with the negative charge is the symbol for the electron. And the charge is -1 negative charge. That's important on the test. You don't want to just say an electron is negative. You want to say it's -1. We want to give that quantitative value. Its mass, which is here, you're not going to need to be able to recite. Relatively, its mass is single 1. Okay, its relative mass is a single 1. Protons, P with a positive sign, with a plus sign, they're 1 positive. This is their relative mass, much larger than the mass of the electron. But these numbers are so hard for our brains to imagine that we like these relative masses. So the relative mass of a proton is 1,836. So if the electron is just 1 marble, okay, then the proton is 1,836 marbles. If the electron is 1 pound, then the proton is 1,836 pounds, 1,836 times the mass of the electron. And then the neutron, which has a symbol of N0 or N0, has a 0 charge. Its mass is very similar to that of the proton, and its relative mass is 1,837 times the mass of the electron. So 1 electron is 1 marble, 1 proton is 1,836 marbles, 1 neutron is 1,837 marbles. So there's one thing I just like to show you guys about how these numbers add up. If we look at the electron plus the proton, if we add their charges, -1 and +1, if we add these together, we get a 0 charge, and that is the neutron. And also, when we do their relative masses, if this is 1 and this is 1,836, then we get 1,837. Again, when we add these up, we get the mass of the neutron. And so one way I think about this is that a neutron, so if this is a proton, and then you imagine like an additional piece right here that is the electron, this whole thing would be like a neutron. And actually what we do see is in radioactive decay, basically a chunk of the neutron breaks apart into the proton and the electron. We can't put them back together to make the neutron like this, but we can see them degrade or break apart to form a proton and an electron. And that's one way that we see nuclear decay over time. So we're going to be moving on to some kind of accounting within the atom, keeping track of the subatomic particles and what that means for the identity of the atom. One thing about this is that it can be a little bit confusing. The terminology sounds very similar. We have atomic number, we have atomic mass, we have mass number, we have average atomic mass. And so it's really important that you are keeping like kind of a running list of what these definitions are, what they mean. I'm going to be keeping something similar on the board behind me. I really highly recommend that you keep a similar kind of running tally of what these different terms mean. So the first term we're going to learn is called the atomic number. And the atomic number is the number of protons in the nucleus of the atom. And this establishes the identity of the atom. So if you find an atom and there are 9 electrons in the nucleus, okay, you find an atom and there are 9 electrons in the nucleus, that atom is fluorine. If you find an atom and there are 6 protons in the nucleus, it's carbon. If there are 3 protons in the nucleus, then that's lithium. And you can know this by looking at your periodic table. And that atomic number is the small number usually written above the elements. Atomic number is symbolized by the letter Z, and this is the number of protons. And typically, you're going to see this number either written, so if you have like oxygen in the square on the periodic table, it's usually going to be up here, 8, okay? Or sometimes it'll be written down here, A to Z. We'll go over that in a minute, but the top number would be the mass number, and then the atomic number would be 8, okay? Carbon, for example, has an atomic number of 6, always 6 protons, and the periodic table is arranged according to this atomic number. So if you go look at your periodic table, which I really encourage you guys to do right now, let's look and figure out where it is in your book. So I'm just looking right here, and it's on the last page of my book. When you look at the periodic table, you will see that the top number is the atomic number, and as you go across from hydrogen to helium, from lithium to beryllium to boron to carbon to nitrogen, you're seeing an increase in the atomic number as you move across the periodic table. I really encourage you to go ahead and look that up right now. Our atoms, we've just established, will always have the same number of protons. The same element will have the same number of protons in the nucleus. The electrons should be equal but opposite to the protons if we're a neutral atom. We said that 2 slides ago, that protons equal electrons. And now we just need to talk a moment about the neutrons, because the neutrons can definitely change. An isotope is an atom that has a different amount of mass than the other atoms. And the only way this mass can change is by changing the number of neutrons in the nucleus of that atom. So atoms can only differ in the number of neutrons, not in the number of protons. Neutrons, because they're neutral, are not going to change the atom's charge, not its identity, because they're not protons. They only change its mass. They make them heavier or lighter. It's like gained a few pounds, lost a few pounds. Okay, same internal mechanism of the atom, same behavior, just the heavier ones will be slower and the lighter ones will be faster. Just in case you're keeping track, atoms can vary in their number of electrons, but we don't call them atoms. If they vary in the number of electrons they have, we call them ions. So in that way, when I say atoms have to have the same number of protons and electrons, that's because if we varied the number of electrons, we don't call it an atom anymore. It's like a syntax thing. It's a word usage thing. So if they've changed their number of electrons, then we would call it an ion. And of course, atoms of the same element can't vary in their number of protons because the number of protons is how they are established. So can they vary in their number of protons? No. Can an atom vary in its number of electrons? No, because then it would be an ion. Can it vary in its number of neutrons? Yes, it definitely can, and it's going to form isotopes. So we're going to look at an example of that. We are looking at the example of hydrogen and the 3 different possible isotopes that hydrogen can form. So hydrogen is here, okay, a hydrogen atom, if you look it up on your periodic table, which you should have nearby at this point, pretty much every time we're going through anything, okay, you should have your periodic table nearby. So hydrogen, it says that its atomic number is 1. So that means that it has 1 proton and 1 electron. That is a standard protium ion. There is another isotope, though, of hydrogen, and this isotope is called deuterium, deuterium, that has 2 things in the nucleus. It has 1 proton and 1 neutron. There is a third isotope of hydrogen that has 1 proton, 2 neutrons, so that makes 3 things, tritium, right? Like the tritium, like Father, Son, and Holy Spirit. The tritium isotope of hydrogen has 1 proton, but 2 neutrons for 3 things in the nucleus. And all of these 3 things are isotopes of hydrogen. So they're all hydrogen. So they all have the symbol for hydrogen because they all have 1 proton, which remember is how the atom is defined. But they're all 3 different isotopes, and they're present in different abundances. So you see this term afterwards, abundance. That means how common is it? So protium, this hydrogen right here with just 1 proton and 1 electron, 99.9% of the time, the hydrogen that you run into is this protium. Only 0.0018% of the time do we find deuterium. And tritium is so rare that we call it trace, which means you can't even give it a percentage number because it's so rare to see it. Doesn't mean they don't exist. They definitely exist. They're around. But these are 3 different isotopes of 1 atom. So they're all hydrogen. That's just the protium isotope of hydrogen, the deuterium isotope of hydrogen, and the tritium isotope of hydrogen. So 3 different kind of terms for the same atom, just that weighs different amounts. So 3 different isotopes. All right, so now we're going to add another one. Remember I said we have all of these kind of confusing terms, overlapping terms. And so the next one is the mass number. The mass number is symbolized by the letter A. And it is equal to the number of protons plus neutrons in the nucleus of the atom. You can think of the mass number like this. It's the 2 things that have the most mass, protons and neutrons. So we're looking at what things are contributing to the mass of the atom, because remember the electron is so small, and that's the protons and the neutrons. The mass number is never shown on the periodic table because the mass number will vary depending on which isotope you're working with. So there's no need to put the mass number in the box. So when you go looking in the boxes on the periodic table, you will not find a box for mass number. The mass number is equal to the number of protons plus the number of neutrons. So if we look at the isotopes of hydrogen that we were just looking at, we start here with protium. It has 1 proton and 0 neutrons. So if we want to find its mass number, we would do 1 plus 0 equals 1. Okay, mass number of 1. So the symbol for hydrogen would be its chemical symbol here, H. And then the atomic number is in the bottom left corner. That's here. And the mass number is going to be above it, up there. So if we're going to include the mass number, remember this is not on the periodic table. This is just if we do the symbol. We would put the mass number in the top corner. What I like to say, or how I like to remember it, is that it goes A to Z on the top. Now, of course, that requires that you remember that mass number is A and atomic number is Z. Let me give you a quick helper for that. Atomic number starts with an A, so it feels like it should be an A, but it's not. I don't know if that's helpful for you, but that's helpful for me. I remember that mass number and atomic number are opposite of what's logical. It makes sense that atomic number would be A and mass number then could be Z, but it's the opposite of logic there. When you're making the symbol, we're A to Z, like you're reading A to Z, right? A at the top, Z at the bottom. So let's look at deuterium. Deuterium is atomic number of 1. So it has 1 proton, it has 1 neutron, which makes 2 for its mass number. So now what we see is a shift in the symbol. So we still have the same chemical symbol, still hydrogen here, H. Same atomic number of 1. Mass number now has increased, so the mass number is 2. Tritium, we'll just move through it quickly, right? 1 proton, 2 neutrons, 3 for the mass number. 1 plus 2 equals 3. And then the mass number goes on top of the symbol, the atomic number is underneath, and then we have the chemical symbol here. So again, 3 over 1. If that's difficult for you to remember where the mass number and atomic number are, I think it's easier, a little shortcut in your mind, is to think of the fact that if one is protons and the other is protons plus neutrons, the atomic number must then, by definition, be the smaller number, because the bigger number is going to be this number plus whatever. So the smaller number in the symbol is going to be your atomic number. So it's a good kind of check for yourself. Another way we can look at this is if I were to ask you a question and give you the mass number, you could subtract. So the number of neutrons equal to the mass number A minus the atomic number Z, that will give you the number of neutrons. Or you could say mass number A is equal to the protons plus the neutrons. And so we're going to be using these two equations kind of moving forward for the remainder of today's video. Okay, so we're just going to look at 3 problems here. The first one says, how many neutrons are present in nitrogen 15? So nitrogen 15, when something is written like this 15 is the mass number. And you can know that, again, because the atomic number for nitrogen is on the periodic table. So if I come onto the periodic table, I see that the atomic number for nitrogen is 7. Okay, Z for nitrogen is 7. The atomic number is 7. So if I want to know how many neutrons there are, remember that neutrons equals the mass number minus the atomic number. So I would do 15 minus 7, 8 neutrons. Now, if you are answering this question, it's really important that you answer it 8 neutrons. Neutrons is the unit. So if I say how many neutrons are present in nitrogen 15 and you say 8, that's only going to get you half credit. Okay, you need to make sure you're putting 8 neutrons are there. Okay, let's try the next one. This one says, what is the mass number of an isotope of lithium with 4 neutrons? So for this one, again, we're going to have to go to the periodic table, find lithium, and see what its atomic number is. Lithium's atomic number is 3. We know that the number of neutrons equals 4. So mass number is equal to protons plus neutrons. So now I just plug into this one. Mass number is equal to 3 plus 4. Mass number is equal to 7. There is no unit that goes with this one. I would recommend writing out mass number equals 7 for a problem given on the test. So go ahead and try this one on your own. This one's adds a little bit of extra because it's asking you for the symbol, but see if you can get it done correctly. So if we look at an isotope of oxygen, so oxygen, once again, this is relying on us to look up on the periodic table and see that its atomic number is 8. Okay, so we would look up oxygen, we would look at that number above it, atomic number is 8. We know that neutrons equals 9, so this is like the problem that we solved before. So we're going to say that mass number, protons plus neutrons, or A equals 8 plus 9, 9, or A equals 17. 9, 9 plus 9 equals 17. 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 9 plus but that's not the answer that I asked you for. What I asked you for was the symbol. So if I'm looking at oxygen, I'm going to have my symbol of oxygen here. My atomic number is in the bottom left-hand corner, and my mass number is in the top left-hand corner. Remember, it goes A to Z. A to Z. Will I ask you to do this? Absolutely. That is definitely something that this sounds like I would ask you to do. Maybe you're just recognizing the right one. Maybe you are writing out the symbol. You should definitely know how these symbols are written. You should make sure you have somewhere in your notes right now that you have this X, A to Z. So whatever the symbol is, mass number on top, atomic number underneath. All right, that'll cover us for today, and I will see you guys tomorrow for more on counting atoms.